And now we're going to switch, not topics necessarily, but viewpoints. And I'm delighted to introduce our next speaker, Professor Andrea Ghez, and she's going to talk about her work on capturing a supermassive black hole. So Andrea, if you're available to turn on your thing, fabulous, and I will leave it to you.
Fabulous. Thank you. It's a real pleasure to have the chance to share the work that we've been doing at the Keck telescopes for the last 25 years. This is a project that started roughly when the Keck Observatory first came into operation. It's actually at the same time that I started my job at UCLA. And the question that we were interested in asking is there a supermassive black hole at the center of our galaxy? And while the answer is so clearly yes today, it's useful to note that, in fact, the first proposal that we wrote to get telescope time was turned down. And it was turned down because people weren't convinced that the technology would work. And there was also sufficient skepticism about the possibility of a black hole. As you already heard from Reinhardt, the idea of young stars being in this vicinity, which was already known, was challenging in the context of the existence of a supermassive black hole because of the strong tidal forces that that black hole would impose in its vicinity, making which would suppress star formation. Okay, so that was the beginning, and yet we persisted. And while the original proposal was for 3 years, it is amazing to me that we are doing this 25 years later with lots more science questions still remaining. So there was really two big perspectives today on why this is an interesting experiment to do. One is from a gravitational physics perspective, which is asking the question, do supermassive black holes exist? And testing how general relativity works or how gravity works in the environment of a supermassive black hole, which before this had been pretty much untested. The second perspective is from an astrophysical perspective, which is to ask what role do black holes play in the formation and evolution of galaxies? And in fact, when the early results from these experiments were being reported, people used to ask at that time, which came first, the central supermassive black hole or the galaxy, somewhat like the chicken or the egg question. And in fact, as a community, we had answers for both. But today we understand that that's simply the wrong framework for the question. We see that, in fact, these supermassive black holes seem to correlate very well with the mass of the central component of galaxies known as the bulge. And these are vastly different scale objects. And so the assumption today is that whatever formed the black hole or whatever formed the galaxy synergistically formed the black hole. And there's some feedback mechanism that keeps the growth of these two objects in sync. And today, the center of the galaxy provides us with a wonderful laboratory for understanding this feedback. Now, it's useful to start off by asking, how did we come to think about supermassive black holes? And in fact, the story of supermassive black holes is quite different than that of stellar mass black holes. The case of stellar mass black holes started from the perspective theoretical calculations, where it was anticipated that very massive stars would end their lives as stellar mass black holes. And that was supported by observations. And in fact, the LIGO, the gravitational wave experiments, has provided exquisite evidence for these stellar mass black holes. The story for the supermassive black holes is very different. They're thought to reside at the center of galaxies, to be roughly 1 million to 1 billion times the mass of the sun. And it was observations that led the way. And in fact, it was observations of active galactic nuclei, which are a small subset of all galaxies, roughly 10%, which exhibit enormous energy, energetic phenomena in the forms of jets that emanate from the center. So this is a radio picture of an active galactic nuclei. So you can measure the kinematic energy in these jets, and that points the way to a very powerful central engine powering these jets. Additionally, the emission at the center of these active galactic nuclei, the emission looks unlike anything emitted by stars or most gas. And that gave rise to the notion that perhaps the emission at the center was accretion onto a very massive central black hole. Okay, so this is a picture at radio wavelengths. So in fact, the galaxy is roughly the scale in here. So these jets are really out, have a much larger scale than the stars in the galaxy. That gave rise, this whole framework focused on active galactic nuclei gave rise to the question, do all galaxies harbor supermassive black holes? And in the case of normal galaxies, ordinary galaxies, these would be black holes that are not accreting. So you could call them stealth black holes. Galaxies are flattened disk-like structures. So if we could get outside our own galaxy and look back, this is very much what our own galaxy would look like. Our galaxy is an ordinary garden variety galaxy, nothing special about us. Our sun and solar system lives about halfway out in the galaxy in a spiral arm. And so our observations at the center of the galaxy are looking from this very low density region out in the outskirts of the galaxy. You could say this is the suburbs of the galaxy towards the center. And you can think of the center of the galaxy as like an urban center. Everything gets more crowded. The density of stars goes up. Almost any way of describing the physical phenomena associated with the galaxy increases as you go to the center of the galaxy. So it's a very extreme and exciting, physically exciting location. Of course, our vantage point is within our galaxy. So looking towards the center of the galaxy, we have to look through the plane of the galaxy. So this is an image from the side of Mauna Kea in Hawaii. This photograph. So you'll notice the plane of the galaxy, the Milky Way. You'll see all the stars here, which are the stars in our galaxy, but presumably you'll also notice that there's a lack of light running down the center of this image. And that comes from all the dust that is in the plane of our galaxy. Now, dust is very good at absorbing optical light. So optical, 1 out of every 10 billion photons makes it from the center of the galaxy to us at optical wavelengths. So it's really invisible, which is what you're seeing here. But if you go longward of what our eye detects to the near infrared, most of the work that we've done has been done at 2 microns. 1 out of every 10 photons makes it to us. So you can actually see the center of the galaxy at infrared wavelength. So in fact, the progress that has been made in infrared detector technology has been a key element of enabling this work to be possible. As Reinhard has already said, the key to discovering the black hole is the ability to see stars that are at the heart of the galaxy. We're going to measure this. We're going to measure the gravitational influence on these stars. Of course, their motions tell you the mass that is inside their orbits. So the proof of the black hole is to show that there's a lot of mass inside inside a very small volume. And in particular, you'd like to get down to the scale of a Schwarzschild radius. In the beginning, doing this on a very short time scale, the goal was just to measure the ensemble average of the motion of stars to get a statistical measure of the enclosed mass. Which is why we thought we could do this in 3 years. That was sort of stage 1 for us. But if you wait, and in fact, early on, if you realize that some of these orbits should be short enough to measure on a human lifetime, and that gives you a much more powerful handle on the mass, because you can overcome the statistical assumptions that you have to make to get the statistical enclosed mass. And those are the kinds of orbits, the eccentricity distribution of the orbits, and then the density distribution of those orbits are underlying assumptions. In fact, the mass changed by a factor of 2 when we went from the statistical technique to the individual masses, individual orbits. The need to get to this, the stars that are as close to the center of the galaxy as possible is what leads you to the need for very large telescopes. The telescopes that we've used are the Keck telescopes. Each telescope has a diameter of about 10 meters, which is like the width of a tennis court. Of course, large telescopes have the promise of enabling you to get to very high or angular resolution. In other words, your ability to see small angles. And this should scale as 1 over the diameter of your telescope. But the problem or the challenge historically for getting to the diffraction limit of these large telescopes has been our atmosphere. The atmosphere is great for us. It allows us to survive here on Earth, but it is an absolute headache for astrophysicists who want to study the universe. This is actually some of the earliest data that we took on the center of the galaxy. It's a picture that's taken, or an image that's taken every 10th of a second. And you can very clearly see the impact of the atmosphere. If there were no atmosphere, each of the 5 bright stars that we're seeing here would be the size of the smallest structures that are dancing around, and they would be rock solid. All right, so the challenge, or what my group's been focused on, is actually how can you overcome the blurring effects of the Earth's atmosphere and achieve the diffraction limit of the Keck telescope. Now, there are a lot of solutions to this, not for the Keck telescope, but in general. And of course, this is getting above the atmosphere is the solution of Hubble Space Telescope and the future James Webb Space Telescope. And this certainly overcomes the distorting effects of the Earth's atmosphere. But it's important to recognize that that these telescopes are actually much smaller than what we have on the ground. So if we can achieve the diffraction limit from the ground, we have much more scientific power. So the first approach was to just modify some existing instruments at the Keck telescope that were designed just to take images without overcoming the Earth's atmosphere. And all we had to do was change the electronics so you could read out fast enough and change the optics so that the pixel scale is much smaller. And then you just take thousands and thousands of frames of these very, very short exposures. And in post-processing, you deconvolve what the atmosphere is doing to you versus what the underlying images is. And this is actually what the both groups did for the first 10 years. So it was very time consuming and only so effective. Nonetheless, it got us the first stage of the experiment, which was the statistical, the velocity dispersion measurements. So time definitely helps this kind of measurement because these stars are, you're going after orbits, but the advancements in technology also have been a huge boost to this kind of work. And after the first 10 years, both groups moved to the technique of adaptive optics. Now, adaptive optics is a technology where you're trying to overcome the blurring effects, the distorting effects of the Earth's atmosphere in real time rather than in post-processing. So if you think of the atmosphere as a single phase screen, you can think of the atmosphere or the wavefront. Actually, this animation is going to show you the path of the light bouncing off the primary mirror, which is how we describe the size of telescopes, into the instrument bay. And of course, there are a couple of miracles that happen in this animation, lots of walls disappearing, but we're going to look inside the adaptive optics system to see the key components that enable the overcoming the blurring effects of the Earth's atmosphere. Okay, in the top right is the key component, which is known as the deformable mirror. This deformable mirror, the goal of the system is for the deformable mirror to take the conjugate shape to what the atmosphere has imposed on your wavefront as it passes through the top of the atmosphere. So in a moment, we're going to see wavefronts that come through here. So they look like Pringles potato chips because the atmosphere has put some air on it. And the deformable mirror now is going to take the opposite shape so that once it bounces off this mirror, ideally, it should look like flat pancakes again. And of course, the key here is some feedback loop that allows you to figure out how to move that deformable mirror. So here you have the cleaned up point sprite function, response of the system to a point source. This speckle imaging, the original system, you could clean up 3% of the light and put that in a diffraction limited core. With the adaptive optics, you get up to today's adaptive optic system, you can get up to 30%. And today's generation of adaptive optics uses a single laser to stimulate an artificial star by stimulating a very thin layer of sodium atoms up at 90 kilometers. And that's the object that we look at to tell our deformable mirror how to operate. So with a single laser, you can get about 30% roughly of the light corrected into a diffraction limited core. So that's where we are today. And that's a huge improvement. So again, this is the image. This animation starts off with what you would see if there were no corrections for the Earth's atmosphere. And then we transition to an image that shows how the image looks if the adaptive optics system is turned on. And the key is in this little inset box. So while we measure thousands and thousands of stars with the adaptive optics system, we're going to focus inside this box for a moment. And in fact, in a moment, we're going to go in even further. But you can see that without adaptive optics or speckle imaging, you can't see what's at the heart of the galaxy. And with these technologies, you can see the stars that are the key to this work. So it's these stars whose motions one wants to observe. Okay, so now we're going to go into a fourth of the real estate of that box. And so this is the animation that shows how these stars have moved over the past 25 years. And I have to say, I could watch this movie forever. Because it both demonstrates that the technology works and that in fact you have the power to show what's driving the orbital motion of these stars. You can probably find my favorite star in the universe. Its name is SO2 or S2. It goes around every 16 years, and you can see many of its other friends that are orbiting in this region. Turns out, actually, about one star every year goes through its closest approach that can be captured by these kinds of observations. This animation also captures a couple of other things. One is that it captures when you can follow a particular star with images. And that's shown with the dashed lines. And once that star can be measured spectroscopically, it's followed with a solid line. And that's important to realize because, you know, these are moving in 3 dimensions. The images capture the positions, or what we call the astrometry, which captures 2 dimensions of the motion. But it's key to get the spectroscopy because the spectroscopy allows you to measure the motion along the line of sight, and that's critical for where we're going in particular. Okay, so at the beginning of this work, actually this is the work of Charlie Towns. We knew that there was 4 million times the mass of the sun inside this enormous region. And in fact, this region is so much larger, many orders of magnitude larger, that in fact, it wasn't possible to claim that there was a black hole at the center of the galaxy. But what the orbits have done for this work is to show that this 4 million times the mass of the sun is confined to a volume that's a factor of 10 million times smaller So this confines the 4 million times the mass of the sun to a region that corresponds to roughly the scale of our solar system. So if you think about our solar system, which is dominated by the sun, one sun, we've now shown that in the same region, there's 4 million times the mass of the sun. This has moved the case for a supermassive black hole from a possibility to a certainty by advancing the evidence by a factor of 10 million. In fact, it's worth noting that the velocity dispersions, that first stage of the dynamical work, moved the case by a factor of 1,000, and it was the orbits that moved it by yet another factor of 10,000. So this has been a radical advance in our understanding of the possibility of supermassive black holes. So we now have the strongest evidence to date for the existence of a supermassive black hole, not only in our own galaxy, but in fact, anywhere in the universe. So today, the goal has really shifted to understanding both how gravity works near a supermassive black hole, as well as the role that the black hole takes on in shaping, or that feedback between the black hole and its host galaxy. And I have to say, this second aspect of the work has been particularly delightful, because it's a great demonstration of how new technologies, which enable us to see things with ever more powerful eyes, opens up the ability not only to answer the question that one first set out to address, but also raises more questions than answers, as has absolutely been the case in this experiment. So I won't spend too much time on this astrophysical part, but it is really, it's incredibly rich. The data sets that we collect allow us to enable to explore many astrophysical questions. So in fact, almost every prediction one can make for what one should see in the vicinity of a supermassive black hole has been inconsistent with the observations. So there's a tremendous amount of work to be done to understand this feedback or coevolution of the supermassive black hole and the host galaxy. This animation, actually it's not an animation, for some reason it's decided not to play, shows a couple of really interesting aspects. One is that the kinds of stars are color-coded by the colors. So the young stars, which we do not expect in this region, given the existence of a supermassive black hole. So the tidal forces are so strong that you would expect, you need gas densities that are a factor of 10 to the 11th times higher, 10 to the 11th times higher than we see today, in order for self-gravity to overcome the tidal forces and enable star formation. So as Reinhardt's already mentioned, we like to call this the paradox of youth. So those are the green blue stars, these young stars that are just a few million years old. People have asked about any alignment in the orbits. And in fact, many of these young stars, when you get far enough away from the black hole, do show a co-alignment, suggesting that the formation of these young stars may be connected or have some connection to how planets form in our own solar system. So in fact, dynamically, the center of the galaxy looks very much like solar system, with a massive dominant central object and objects orbiting it. In fact, the mass ratio of planets to the host star is very similar to these stars and the supermassive black hole. So dynamically, there's a lot of crossover between these fields. The second kind of stars that provided us with fodder for thought are the orange stars. The orange objects are the old stars, the stars that are roughly 1 billion years old. And of course, we identify what's old and young through their spectral characteristics. These old stars, the prediction is that they've had lots of time to dynamically interact with their environment, and through dynamical friction should migrate into the center And there should be an excess of old stars around the supermassive black hole. And in fact, that is how black holes and many other galaxies are identified, by looking for this enhancement of light at the center, known as a cusp. So it's really interesting that in fact, there's a dearth of these old stars that are seen with today's technology. So that's puzzle number 2. Where do the old stars go? And then puzzle number 3, which today I have to say is one of my favorites, are the magenta objects. The magenta objects are actually showing tidal interactions. These are the first spatially resolved tidal interactions that have ever been seen around a supermassive black hole, and they're very unexpected. These objects survive their closest approach, which suggests that there has to be a star keeping the object together. So you see them come in, you see them elongate, go through closest approach, and then as they proceed back out to their furthest approach, they become compact again. In order for that kind of interaction, that tidal interaction to occur, these objects have to be about 100 times larger than any of these other kinds of stars that we predicted to be there. And that's incredibly interesting. And one of my favorite ideas that have been proposed for this is that these could be pairs of stars, binary stars, that have experienced an interaction, a three-body interaction with the central star, known as the Kozai-Lidov effect. And that can pump up the eccentricity. You get exchanges of the eccentricity between the small pair of object and then the orbit of the binary around the black hole. And pumping up the eccentricity can cause those objects to merge. And when they merge, they blowed up by a factor of about 100 for roughly 100,000 years. So that could easily explain these tidally interacting objects at the center of the galaxy. And what's particularly exciting to me about this idea is that provides a connection for perhaps for what's being seen in the gravitational wave community, with stellar mass black holes becoming much larger than was anticipated and at rates that were much higher. So perhaps we're seeing at the center of the galaxy a physical process that may be related to what causes the kinds of black holes that are being seen by LIGO and Virgo. Okay, so that's the astrophysics, and in fact, there's even more in terms of the black hole accretion on itself. But what I'd like to turn my attention now to is the story of.
Sorry about
Thank you.
Sure.
Yeah. So what we'd like to do now is look at what is the potential for these stars for probing how gravity works near a supermassive black hole. And as you've already heard, there are two particular probes that are within reach of today's experiments. It's also worth noting that to get a seat at the table to do these kinds of experiments, one has to have a measurement of the complete orbit. And then the next time it goes through its closest approach is when you get a seat at the table or a view or a handle on how gravity works, because you need the shape of the orbit. In other words, you need to know where this object is in space and time to get a handle on these relativistic quantities. So the first one that becomes accessible is the gravitational redshift, which describes the impact of the curvature of space-time on the photons as they proceed from the object itself. And of course, it's the strongest at closest approach to our telescope. And then the next one that becomes visible, but is a harder measurement to make, is the precession of a periapse. So that's the rotation or the precession of the orbit. And general relativity predicts that these orbits should precess in a prograde direction. As you've already seen, what was anticipated in terms of the gravitational redshift has been beautifully confirmed with the observations. It's important to remember that to do this, you need both the images and the spectra to get a handle on the shape of the orbits. But what we're showing you here is the deviation of the radial velocities, or in other words, the spectral line shifts with respect to the Newtonian best fit orbit. It definitely confirms it, but it's important to note that what dominates the sources of uncertainty here are, in fact, our knowledge of the orbits. And I just want to highlight here that in terms of comparing the various measurements, it's useful to remember that there's 17 parameters, or there's, at least in our models, there's 17 parameters, and it really depends on what kind of priors that you impose on any of these measurements, and that systematics actually dominate these measurements. We're getting into the regime of precision measurements, as Dr. Gates alluded to at the beginning of the session. If you look under the hood, and I think it's useful to look under the hood, if you look at what's coming out from the two groups, well, the redshift, if you just marginalize over all the other 16 parameters, the redshift looks like it agrees. But if you start to look at the individual properties, there is some disagreement. And this just shows the original publications. And there are a lot of places that you can look for these systematic errors, including instrumental changes, understanding all the correlations that run throughout this experiment. And the thing that actually, I have to say, keeps me up at night, which is something that's called the astrometric reference frame. How do you get 25 years of data into a common reference frame? This becomes incredibly important when you go to the next piece of this experiment, which is the procession of the periapse. So while you can put uncertainties in the reference frame into a parameter for the redshift, you cannot do that when you're talking about the procession. And in fact, our early results, and I want to say this is early because we have not published this yet, it's the orbit actually seems to be processing in the opposite direction at twice the speed. Okay, so that's puzzling. And there are a lot of ways in which one can go wrong experimentally. But if you want to interpret this physically, you can do so in the form of an extended mass. And depending on what you assume for that concentration of the cusp, what we saw in luminous matter as being missing could be actually there in the form of dark matter. So perhaps this is what's actually causing this to open up in the opposite direction. But it's really early days. And in fact, one has to truly recognize that it's easy to go wrong with the reference frame. You have to put 25 years of data very precisely in a common reference frame. So the future of this is always technology. So multiple lasers makes a difference. You're doing a CAT scan of the atmosphere, which gets you much higher performance and is absolutely essential if you want to get to the next generation of telescopes. So this next generation is currently being built at CAC. It's a collaboration actually between all the adaptive optics players for the next generation of telescopes, the TMT, GMT, and the European Extremely Large Telescope. So it's really nice to see these teams collaborate, and it'll allow us to see the more common star. Today, we're only seeing the tip of the iceberg. This future generation of experiments will allow us to see the much more fainter and much more common kind of stars, and will hopefully allow us to sort out what's going on. I just want to end with acknowledging that this has been done in a collaboration. I feel very grateful to have successfully collaborated for 25 years with a wonderful team of people. This project started off with a team of 3 faculty, so Professor Mark Morris, it's shown here in the middle, and Eric Becklin, and then along with my very, very first grad student. So it was a very small team to begin with. Today, we're an extended collaboration, of core collaboration of 30 with a broader network of roughly 100. And I really want to highlight, in particular, 2 people, Jessica Liu and Tuan Do, who started off as grad students and are now faculty with their own grad students involved in this project. So let me end by saying, if nothing else, I hope that we've convinced you that there's a supermassive black hole at the center of our galaxy, and that we've actually opened more questions than provided answers.
Thank you. That was a lovely talk. Absolutely beautiful images. I'm sure everyone enjoyed that tremendously. And you've gotten a lot of thank yous in the chat window. If I can, I'm going to start asking you the questions that people have posted. One of them is, what are the prospects of measuring supermassive black holes in the centers of other galaxies, say using the future 30-meter telescopes? And what's the limiting factor?
So resolution is the limiting factor. So certainly you'll get to the point of the first phase of measuring velocity dispersions, but measuring individual orbits is not within the reach of even this next generation of telescopes for more distant galaxies. So our galaxy is really unique in terms of being a laboratory for using orbits to understand supermassive black holes.
Thank you. Two people are asking about the mass gap between stellar black holes and galactic black holes. They're curious if that's due to observational bias or some well-understood gap.
Oh yeah, so this is a really interesting gap, the idea that there might be intermediate mass black holes. People have often wondered whether or not you might find intermediate mass black holes at the centers of globular clusters. And in fact, there have been a couple of tentative cases for such systems. Now, the challenge, of course, is always that the velocities are smaller and that you're always using just a few stars. So I think that's it's another arena in which the next generation of telescopes may indeed really help us get a better handle on that.
What is the deformable mirror made of, and how do you control deformation?
Oh, that's a great question. So a deformable mirror, one of the things you might ask, why not use the primary mirror? Because Keck is a segmented mirror, but in fact, those segments are so heavy that you can't move them around quickly enough. So there's an active control system on the 36 segments that make up the primary mirror, and they move around at a rate of roughly half a hertz. The deformable mirror is much smaller, and in fact, it's about this big. It has 360 segments, at least the one that we use at Keck today, and it's moved around with little piezoelectric that allow us to correct at a rate of about 1,000 hertz.
I muted myself. Derek Kimball says, thank you for the wonderful talk and thrilling work. What, with the correlation between the host galaxy bulge and the supermassive black hole at the center, and the role of dark matter in galaxy formation, is there a possibility of dark matter playing a role in the supermassive black hole formation?
Absolutely. And in fact, we think it's really essential in terms of our whole understanding of how galaxy formation gets going. Is we understand that today we believe that it's dark matter fluctuations that really lead the way to the formation of the galaxy. And in fact, this connection between black holes and the bulge suggests that the dark matter is key to the formation of the black hole as well. So in fact, early on, one of the questions was, could you see dark matter through these orbits? Today, I suspect that it's going to be dominated by the form of stellar remnants rather than dark matter. But there's also been some really interesting work thinking about the possibility that these stars' appearance could be altered by being these objects being infused, dark matter infused objects. So could you actually change the stellar evolution and hence appearance? Because of course we're interpreting these stars, their masses and age by comparison with stars that are out in the out by us.
There's so many great questions in the chat. I apologize to both the listeners and you that I can't ask them all, but it's 9:43 and it's time to go to our third speaker. But thank you so much, Dr. Ghez. That was wonderful. We appreciate it. Another round of applause.